Looking at the sine of f prime method for finding absolute extremes. And to illustrate this method, I'm going to consider number 10 on page 226. So if you have your book, go ahead and turn to page 226.
Thank you, man. Please, what's today?
Okay, so we have the problem here, which all of you can read. And so we are going to focus on two different issues. The first issue is translating our English into math. And if you watched the video last night, that was where a lot of our effort was expended on the process of translating English into math. And the second thing that we're going to do is we're going to find that our critical points and endpoints method doesn't work here because we don't have any endpoints. And so we're going to need to argue in a different way to argue that our absolute max is in fact the absolute max that we're looking for. And that argument is going to be an argument in the sign of, in this case, a prime, or the derivative of the area. So here we go. Let's work on the translation problem first. We're told that a 216 square meter rectangular pea patch is enclosed by a fence. In order to make sense of this problem, I immediately want to do what for myself? Draw a picture. Very good. That's exactly it. I'd like for everybody to draw a picture of our rectangular pea patch. Some pictures are better than others. The picture on the left is not going to be helpful to us because it doesn't have the crucial pieces of information that are going to be needed in order to solve the problem. The picture on the right is going to be helpful to us because it has two important things. It has the area listed inside here as given. And it also labels the sides of the pea patch. I didn't know what the sides were, and so I called them something. This is the basic thing that we do in math, right? You don't know what something is, you call it. And so I called them X and Y. You might have called them M and N, or Fred and George. I don't care, as long as you're calling them something. And now we're told a second thing, that it is divided into two equal parts by another fence, parallel to one of the sides. Go ahead and draw that situation. I sure can. So take care of the language underlined in red there. As soon as you start to do it, perhaps you get confronted by a confusing question. What is your confusing question? Which way does the fence go, right? As soon as you get hit by that confusing question, now we ask ourselves another question. Does it matter if it's square? Well, it's a rectangle, but it's meters squared. Yeah. Does it matter? It might not matter. So let's see if we can argue as to why it wouldn't matter. If I draw my side like this, I'm going to end up computing values for x and y. And if I have it the wrong way, I'm just going to find out that x is larger than y. In which case, I simply have to extend my drawing a little bit, and now it looks like the other drawing on its side. In other words, the choice of which way to draw the line doesn't matter because the computations will take care of it. Does that make sense? How many of you were hit with that confusing question? Yep. Okay. It's happened to all of us. We all just try to make sure it doesn't happen during church. Okay. Now, as soon as I draw my side, how many of you ended up drawing the side down horizontally? And how many of you drew it vertically? No problem. If I draw it horizontally, how am I going to label that side? X. Exactly. If I drew it vertically, then how am I going to label that side? Y. That's right. That's right. The area of each one of these parts will be 108. Yeah, that's exactly right. So I can do that, and I can do that for myself. I'm not going to end up using that fact, but noticing it is a good thing. Okay. And now they ask, what dimensions for the outer rectangle will require the smallest total length? And there it is. That word smallest is the key word that gets my attention here. That tells me I am looking for an absolute minimum. And specifically, I'm trying to minimize my length. Of fence. And how much fence will be needed. Okay. So let's immediately now take our diagram together with what is asked and construct everything. The first thing I need is I need length. And the length that I have is going to be found from the diagram. Let's go back to the diagram and ask how much total fence does this diagram tell me that I need? I need x. Another x would be 2x, 3x, plus 2y. That's exactly right. If you have a vertical line, then your length is going to be 2x plus 3y, right? And that's okay as well. We're just going to get opposite labels for our final values. Okay? So I am trying to now find the absolute minimum of this function L right here. But wait, there's more. I am also told that the total area of this rectangle is 216, and I want to translate that from English into math. Let's translate right here. There isn't any word here that indicates that I would want some kind of a max, right? There's no largest or anything. Instead, it tells me that the area is 216. So let's translate that from English into math. What is the area of a rectangle? It is x times y. And what does it mean that the area is 216? It means that x times y equals 216. That's exactly right. This is the translation of I have 216 meters squared of area. And so because I have an equation, a relationship between x and y, I can now substitute for y or for x by solving for y or x and plugging into my length right here. And when I do, That's 432 over x, just like this. And this is now the length function that I have for the total amount of fence based on just the variable x. It is important that I have just one variable, because if I had two variables, I wouldn't know how to take a derivative of it, right? You're not going to know how to take derivatives of functions of two variables until you take Calc 3, which is way ahead in the future for you. So we needed one variable, and substitution was how we made that happen. Okay? Now, at this point, I'm just looking for the absolute max of this function. So you guys know how to do that already. Coach me through the process here. I want the absolute maximum of length, so how do I go about it? I need a derivative. And so we have dl dx equals, term at a time, the derivative of 3x is 3. I'm going to think of this as 432 times x to what power? To the negative 1. So that its derivative is negative 432 x to the minus 2. Or 432 over x squared. Now that I have the derivative, what do I do with it? I set it equal to 0 to find critical points. This is a kind of awkward equation, so I'm going to clear the fractions by multiplying both sides by x squared. And when I multiply both sides by x squared, then I get 3x squared minus 432 is equal to 0. Looks to me like I could factor out a 3, right? And that would give me 144. How does x squared minus 144 factor? Yeah, x minus 12x plus 2. What you got?
When you have dl dx equals 3 minus 432 x to the negative 2.
Yep.
How do you go for that?
I realize that 432 over x is the same as 432 times x to the minus 1 power.
Oh, right, okay.
And then I use power rule on that. Yep. Very common move there. Yep. Good. What do you think about these two critical points?
Okay.
They are not equal. They're not both equally useful. What would it mean for x to be negative 12? I would have a negative, not area, but a negative width, right? And it doesn't make sense for me to have a negative width for my garden. Okay, so I'm going to exclude x equals negative 12 on the grounds that it is outside of domain. So I've got a critical point. Are there any other critical points besides x equals 12? We checked for when the derivative equals 0, but we must also check for when the derivative does not exist. Are there any places where the derivative does not exist? When x equals 0, bam, I blow up. So we would say that dl dx does not exist if x equals 0. So I have these two critical points right here. Now I begin to think about endpoints, and I think to myself, what is the domain of the problem? What is the smallest value of x that I could possibly have? And the smallest value of x that I could possibly have would be to shrink x until it is all the way to 0, right? In other words, I would end up with this sort of degenerate p-patch that was infinitely long in the y direction and 0 width in the x direction. What's the largest value of x that I could have? Well, x could keep on getting larger and larger as long as y shrinks to match it, right? So there is no endpoint for our domain. We can't use a critical points and endpoints method. So what are we going to do instead? Instead, we're going to consider the sign of dl dx. Let me make a number line for L prime right here. And I'm going to put my critical point of 12 on it. I'll put the critical point of 0 marked with an X on it, where my derivative does not exist. And I'm going to consider the sine of L prime for x's between 0 and 12. To do that, I need to consider a value of x between 0 and 12. Somebody give me a really easy value of x between 0 and 12 that I can work with. I like 1. Because I can see that dl dx at 1 is going to be 3 minus 432 over 1. Is that a positive value or a negative value? It's a negative value. And because my derivative is negative at 1, it must be negative at all values of x between 0 and 12, because it can't go from negative to positive without crossing through 0. And I know where my derivative is 0 at 12. Okay. Give me a value of x that is larger than 12. 1,000,000. If I plug in x equals 1,000,000 here, square that, divide 432 by 1,000,000 squared, I'm going to get a number that's basically what? Basically 0. 3 minus that, is that going to be positive or negative? It's definitely positive. And therefore, my derivative is positive for all x's bigger than 12. Does everybody see the logic, how we construct the number line? And now I'm going to make a really simple argument. My length decreases from 0 to 12 because its derivative is negative, and then it increases from 12 thereon. Draw a graph in your head. My length goes down to 12, and then it goes back up. Where does its absolute minimum have to be? Right at 12. This is an argument from the sine of L prime. And here's how I state it in formal legal language. We're going to say that L of 12 is the minimum because L prime is less than 0 for x less than 12, and L prime is greater than 0 for x greater than 12. This is the argument from the sine of L prime, and it always takes the same form. I argue for a max or a min because my derivative is negative on one side and positive on the other for the entire interval. It was necessary that I use the argument from sine of L prime because I had no endpoints. However, I can use the sine of L prime argument anytime I have one single critical point, whether I have endpoints or not. So this is actually a more flexible argument. It just has one limitation, and that is that it only works if you have one critical point to consider. If you have more than one critical point, then your derivative can change signs more than once, and you might not know where the absolute maximum is. Does that make sense there? I wish we had a little more time to practice this. We will practice a little bit tomorrow. Hopefully we will have a full day, and I will see you later.
Today was just